All right, got a lot of questions by email this morning, so let's start working through them. And yes, I do see the questions in the chat. We'll get to the email ones first. So first question, test 4 on page 25, page 26 of the solutions could be that we could just start react the starting molecule with Br2. So the molecule on page 25 here is this one. And if you were to react this with just straight Br2, this is an anti-addition. And so this would be your final product. And this is what this problem is trying to get you to see, is that if you were just trying to do this with straight bromine, you get an anti-addition and it wouldn't work. They would be on opposite sides of the molecule. So you actually have to go through this halo hydrogen intermediate first, because this is also an anti-addition. And then something like PbR3, this is selective to stereocenter inversion, so it would invert this. Let's say this was an S, it would invert it to the R, and so these two bromines would be cis on this particular bond. So to answer your question, no, you can't react with straight bromine because bromine is an anti-addition. It would need to be a syn addition in order for that to work. Next question, page 29. And 31 in the solution packets. So it looks like the key does actually flip starting molecules. That's a shame. Actually, it's probably supposed to start with both those starting molecules looking at it. And then, so yeah, that just looks like a mistake. In the starting molecule should have an additional carbon. So right now it's 1 butene. It should be 1 pentene. That's just a typo in the key, or that's a typo in the solution set. Another question about page synthesis on page 29. Again, this is kind of just a typo in the key. It should actually be not 1 butene, but 1 pentene, and then everything else that follows in the key actually does work. So you use things like NBS, and NBS here will give you the brominated product. You do elimination here, so terpbutoxide. This will give you the 1,3-pentadiene. React this with, it will rotate to do this. React this with ethylene. This will give you the cyclohexene, and then you can hydrogenate. So the key is correct, it's just the starting molecule is incorrect. So the next one is off the discussion board. It's a PDS. It's going to take a minute for it to load up on my end. So the discussion board this week, I mean, we can go through it. Okay, I see the person's question. Okay, so discussion board this week for organic. You start with methyl cyclohexane and you react it with chlorine and light. You're going to assume monohalogenation, and so first one here is going to be your 1-chloro, 1-methyl, and then you use a strong base to protonate or to eliminate, and this will give you 1-methyl cyclohexene. And we're going to repeat this process with NBS or Cl2 light. Now there is a bit of a problem with this step is that it could either halogenate both of these. We're going to assume it primarily hydrogenates. Well, actually, it really doesn't matter which one hydrogenates or halogenates. But you are given a list, and that's one of the options you're provided with. Oh no, you're given Cl2. No light. Okay, that makes a lot more sense why you would do that. And then you're going to do strong base again, and this will give you your diene, because you can't, this can't eliminate back here because there's no hydrogen, so this is going to eliminate down, this is going to eliminate down the left. And so you've got these two alkene intermediates, and you're asked to figure out which of the products it could be. So the product of any Diels-Alder is going to be a cyclohexene. But the thing is that we've got our diene, so we can build a Punnett squared. We've got a situation where we've got a methyl group up or a methyl group down. Because we can rotate it through there. So we can either have, for our diene, we can have the methyl group on the third carbon or the second carbon. And for our dienophile, we can have the methyl group on the alpha or the beta carbon. So we have 1, 2, 3, 4, 1, 2, 3, 4, alpha, beta, alpha, beta. So now if we draw our cyclohexene products, alpha, in this case, will have the methyl group here. In this case, the beta will have the methyl group down. And then when it comes to these, the first and fourth carbons are bound. So we're going to have this bridge. Oops, got my double bond in the wrong place. And we have the option of having the methyl group down, or the methyl group up. So these are your possibilities. Oh, also the alpha and beta carbons are connected, so there's like rings. And so you end up with a lot of possibilities. The thing to keep in mind with all of these, though, is that you should have two methyl groups present in your molecule that aren't connecting each other. One's connected to the double bond, one isn't. And so if you look at the possibilities, like A, there's 3 methyl groups. There's no way you produce 3 methyl groups because each of your starting alkenes and your diene and your dienophile only have 1 methyl group. There's no way you're going to finish with 3. So that's a pretty quick way to eliminate possibilities with this, is how many of these potential candidates have way too many methyl groups. And I'm guessing the question that I got asked by email is they're looking at the wrong dienophile. So the methyl chloro doesn't have a double bond on it, so it can't participate in the Diels-Alder reaction, so it won't react. So hopefully they answered that person's question. All right. Can you best simplest way to determine if what is R versus S in the enantiomer, like 3S, 4S dibromocyclohexane versus 3R, 4R dibromohexane? So in all cases, we're going to let the CIP rules, the Cahn-Ingold-Prelog rules, work. The way I think about it, so we'll look with the 3S, 4S dibromohexane. So I'll draw the hexane, 1, 2, 3, 4, 5, 6. And versus 3R, 4R dibromohexane. You'd need to spell, 3 and 4. So in order to figure out which one's which, what I find easiest is do the wedge. So draw as a wedge first and figure out if you've got an R or an S. Because the thing about the wedge is that if you have the wedge and your dash here is a hydrogen, that automatically puts the lowest priority group at the back. So this is already set up in order to do basically the clockwise, counterclockwise. So I'll start with the third position first. So if we look at the third one, we're going to go by atomic weights. Bromine's the highest priority, and our hydrogen's the lowest priority in the back. Now, these two are carbons, they weigh the same thing, so I look at what's bound to them. This one has a bromine bound to it. This one has two hydrogens and a carbon bound to it, so this is going to take the lower priority, and this is going to take the higher priority. Now, if we didn't have any other bromines in this molecule, the longer chain is the higher priority, or the one that branches first is the higher priority. So if I look at this, it goes 1, 2, 3, that's counterclockwise. This is the S conformation. So for this third carbon, I currently have it drawn with a wedge as S. Now if I go to the fourth carbon, again, if I start with it as a wedge, the hydrogen's in the back, so this is automatically set up to do that clockwise, counterclockwise, because the lowest group's in the back. Bromine is the highest. This brominated carbon's the second highest. This CH2 group is the third. If I look at it, that's counterclockwise, so this is S. Now, wedges and dashes, if you flip them, will get you to the other one. So if I want to draw the R, I just flip that from a wedge to a dash. So this would be the R and the R. Yeah, this would be R and R. If you want to do R and S, and let's say you drew this as your first guess, well, in order to flip from an R to an S, all you gotta do is change the wedge to a dash. So let's say you want to do SR or RS. That's all you have to do. So when I draw these out, if I'm asked to draw like the R or the S conformation, the first thing I'll do is draw them all out as wedges, because it's really easy to figure out the R and the S at their wedges. Now, if I draw it out and it's an R and I need an S, I just change the wedge to a dash, and vice versa. If I draw it out with a wedge and it's an S and I need to go to an R, I just switch the wedge to a dash. So for me personally, that's the easiest way to draw it from the name. As far as coming backwards, like so taking this formula and going back, I've done it enough times now I can kind of see it on the board, but that's not fair to you to say that. So what I would say when it comes to the molecules, use your modeling kit to do the RS. So the same thing you did for test 1, test 2, and test 3. Build your model kit, identify the priority of the different groups, and then hold it up and manually twist it so the lowest priority group's behind you, and do what I just did up here. But again, for drawing from the name back, I put every stereocenter as a wedge because they're the easiest to look at and figure out if it's R or S. All right, one more question before I get to the chat. Why did I rationalize that? So there's an NMR problem. On page 21, and it asks you to figure out which one is the right one. And the student says the key says B, but their spectrum says C. I think the key is actually wrong because the key should say B. I've worked this out, or the key should say C. So I'm guessing that it actually should say C in the key. It's probably just a typo. But let's go through this page problem to figure out like why it is what it is. So on page 21, you're given 3 possibilities. And we're not going to bother with the stereochemistry because it doesn't matter for this one. And so let's just look at the areas of the peaks. So we expect to see 1, 2, 3, 4, 5, 6 NMR peaks with areas 1, 1, 1, 2, 2, 2. This we expect to see 1, 2, 3, 4, 5 NMR peaks with areas of 1, 1, 2, 2, and 2. And then with this one, when we look at it, we expect to see 1, 2, 3, 4, 5 peaks with area 1, 1, 1, 2, and 2. Actually, no, the key is right. So if we look at the area of the 1H NMR spectrum, we have areas of 1 to 1 to 2 to 2 to 2. There's only one molecule here that has those ratios. This has 6 peaks, so this isn't possible. And if we compare these two, it would be an area of 1, 1, 1, 2, and 2. This would be an area of 1, 1, 2, 2, and 2. So this ends up being the correct answer because it's the only one that gives the correct integrated areas. So this is solution C. So yeah, the key's wrong. It shouldn't be B, it should be C. They may have gotten rearranged in an early draft of the problem sets, but yeah. Now for the questions in the chat. How do we do NMR questions of alkenes? Same way you've done it for alkanes, alkyl halides, alcohols. You need to have a model to guess off of. And like you just kind of saw with this problem, integrated areas are super useful. Looking for singlets is super useful. Counting the number of unique signals. If you see a big molecule but a small number of peaks, that indicates a high degree of symmetry, and so you need to look for the most symmetric molecule. But it's pretty much everything you've been doing so far in the semester. You need a model to go after. So you take whatever potential answers you're given and you try to predict areas, number of shifts, the nature of those shifts, and from there you can figure out which molecule is consistent with that NMR spectrum. Multi-step reactions, study packets, how many products we write in each step, includes stereochemistry for each step. I would say for you that would be very helpful to do. So for me, I find getting students to learn the reactions helps best when you do the mechanisms and when you write out all the potential products that are likely to exist. This is simply a way of contextualizing the synthesis. If you look at the syntheses in these packets, and you'll see with the final exam packets, no one would ever do like a 12-step synthesis. They're super complicated and they're prone to mistakes, and you'll have super low yields. We do this as a way of forcing you to learn what the reactions do. Now, exam is going to be a lot like the last exam you took. Synthesis will be at most 2 to 3 steps. You do need to write out the intermediates to show that you understand what you're doing. But as far as specifying stereochemistry, you'll see notes occasionally written in the packet saying the stereochemistry doesn't matter. It's important that you know what the stereochemistry is because it's going to help you understand what the reactions do. But the thing is that if we're creating a stereocenter and then destroying it regardless, it doesn't really matter what that stereochemistry was. So for all intents and purposes, yeah, you should know it. But also for all intents and purposes, if the stereochemistry is just an intermediate step and it gets destroyed in the end product, it doesn't really matter. All right, for Simmons-Smith reactions, we put wedges or retractors or straight line when CH2 is added. Typically what you'll see textbooks do is they'll leave off stereochemistry because it's a mixture of both. So when we do Simmons-Smith, we're going to end up with a mixture of both R and S. But what you'll see a lot of books do is they leave this off, and this is what's called the relative configuration. So all the way back to test 1, we talked about absolute versus relative configurations. In the absolute configurations, you're specifying wedges and bonds. Typically, you do this because you have a chiral center, either R or S. Relative configuration doesn't specify what the stereochemistry is. And you'll see this done for 2 reasons. 1, because the stereochemistry doesn't matter, or 2, you end up with a racemic mixture, and it doesn't matter that you've ended up with a racemic mixture. So for this one, this is an achiral molecule because it has that mirror plane. So this ends up being a meso complex. It has chiral centers, but those chiral centers are opposite signs, they're mirror images, so it doesn't matter. Also, if you have a terminal alkene, because your terminal even with terminal alkenes, typically what you end up with is at least 1 chiral center. So include it if it is relevant or if it is asked for. But generally speaking, you'll see a lot of textbooks just drop it all together because, yeah, it's there. It doesn't play a huge role in the reaction. Will extra credit be provided? Same as last exam. You have the option of doing harder synthesis problems for 5 or 10 additional points. When do we use Schonk or Grubbs? Does it matter which one you use in writing synthesis? For the reactions we're doing, it doesn't. Now, in practice, Schrock and Grubb catalysts do serve different purposes. The Grubbs catalyst is the superior metathesis catalyst in that it is more versatile. It doesn't decompose in water and air, unlike the Schrock catalyst. The Schrock catalyst is good for very sensitive functional groups. So that's what makes the Schrock catalyst so unstable in air and water, is that it readily reacts with a lot of things that contain oxygen. But if you have a very delicate functional group, so let's say you have a lot of esters, you've got a lot of alcohols, you've got a lot of things that you don't want messed with or to interact with your catalyst, Schrock's the way to go. But if you're looking for a more kind of like all-purpose catalyst, the grub's going to work. But for this class, it doesn't matter, because we're not like, so when the grubs and Schrock catalysts are used in industry, they're used for pharmaceutical drugs. Those are very delicate molecules that you're working with, and so you want to make sure you pick Schrock or grubs based on the functional groups that are present. We're not working with complicated organic molecules that have a lot of complicated functionality. So honestly, they will both do this just fine. The point is that you are aware of what a metathesis catalyst is, a few examples of them, and what the end product is. But again, it doesn't matter, because we're not working with cases where you would want to delineate between using a Schrock or a Gubbs catalyst. NMR alkenes, does double bond between the two carbons deshield? Yes. This is a weird effect. And because when you think about it, when we think about shielding and deshielding, we think about the number of electrons around a given atom. And so you would think by having this extra layer of electrons around this, they would be more shielded. They actually end up being more deshielded. The argument for why it happens, that isn't really the real argument, but it explains it well enough. If you look at the oxidation states, carbon here is in a -4, here it's in a -2, or -3 down here. So we are technically oxidizing carbon doing this. We're reducing the number of electrons. So since it has a more negative oxidation state, we expect this to be more deshielded than this. The reality is far more complicated. These p electrons actually have some degree of lability, and because of this, they can actually align to the magnetic field. There's a complicated effect, and this will actually come up when you go to Organic 2 and you learn about aromaticity. Once they start going into these pi bonds, they get a bit more mobile. And because they get more mobile, these electrons have the ability to interact with the magnetic field and actually have a habit of reinforcing the magnetic field. So the easy answer, which isn't correct, is that oxygen here is a more negative oxidation state here. The correct answer is that these pi electrons are more mobile and they actually work to enhance the magnetic field felt by these nuclei. Difference between NBS, BR2 with light. N-bromous succinide is a much better halogenation catalyst for two reasons. One, it is super selective. It not only does it just do halogenation, it only does single halogenation, and it will only do next to double bonds. This isn't true of BR2 with light. BR2 light will halogenate anything if you give a sufficient light source to form the free radicals. So something like ethane, propane, butane, your alkanes, I don't think you can halogenate those with NBS, at least not readily. And if you were to halogenate them with NBS, it would be monobromination. When it comes to BR2 and light, you can actually do complete halogenation with BR2 and light. NBS will stop at a single halogenation. How do we interpret the infrared mass spec of alkenes? The short answer is there's not a good way to do it. Alkenes are not very... You'll have textbooks claim that you can use IR to identify alkenes. They're not technically wrong, but they're just also not technically right. What I mean by that is the functional group region of the... So there's two parts of the IR spectrum. There's the functional group, and then there is the fingerprint region. So for the fingerprint region, you can 100% identify an alkene from the fingerprint region, just like a mass spec. There is a unique picture beneath the 1,000 wave numbers. But as far as tweezing them out from the functional groups, which is what a lot of textbooks teach IR to do, they're not that useful because the bending modes are actually very small. And they are small for two reasons. One, alkenes just don't interact with infrared spectra that strongly. The second is that the alkene is typically a minority functional group. And so if we just assume that all functional groups acted equally. So we've got this one functional group here, and we've got these two here. This is already a 2-to-1 ratio in the IR spectrum. And the truth is that this doesn't respond nearly as strongly as these two do. So if we look at the ratio of peaks, it's going to be much greater than 2-to-1 in the IR spectrum. The other thing is that they're not strong peaks. They're very small and they're very short. So they tend to get kind of lost into other features. At least in my experience, they get lost in other features. So mass spec is not, infrared is not the best way to really test for alkenes. Some books will contend it can be. My argument is that you would need to know it was an alkene to know what peak you were staring at. Now, if you know it's an alkene, you know those alkene binding modes can be in there, then you can start making arguments like, oh, it's cis or trans based on certain peaks, or you can make the argument that it's conjugated, unconjugated. We'll talk about that in organic too. But the short answer is infrared is not very good for it. Mass spec's kind of the same story. If you use the full mass spectrum and you use a database, it is 100% proof positive for certain alkenes. But if you're just comparing an alkene to an alkane with no information, it's not that useful. And the reason it's not that useful is that you're eliminating 2 hydrogens, that's 2 AMUs. Well, you can also get that by making a ring. So you would have to know something about your material before you could ever say, oh, this is the mass spec of an alkene. Now, alkenes do affect the stability of functional groups. They actually do a really good job of stabilizing charges. So an alkene will cause the fragmentation peaks to get bigger. But again, you would need to know it was an alkene. There are other ways to stabilize fragments other than alkenes. So the main use you would use for an alkene is verifying that you had the elimination product. So let's say you want to know if you made this compound and you start with this compound. Well, if you know this is the only possibility, then you look at the weight differences. You say, did I lose 36.5 AMUs? Now, between this and this, you can't tell the difference looking at the mass spec just based on terms of parent mass, because these two weigh the same thing. But if you had a copy of the fragmentation patterns, which most people do, they compare it to a database, you can compare the fragmentation patterns of this to this to figure out which one you got. But mass spec is more used for, like, infrared and mass spec, I would say, are much more used for relative comparisons. So you take your starting compound and you run a mass spec of it and you run an IR of it, and then you compare it to the product. If they're the same spectrum, you know no reaction occurred. If they are different and you suspect that you made an alkene, well, you can look for the alkene binding modes in your final product, because you can explain a lot of the other peaks. So an example of this would be, let's say you ran an alcohol against sulfuric acid. Or not even sulfuric acid. Let's say you ran this reaction. And you said, well, there's 2 possibilities, because I'm gonna work with really concentrated HCl here. I could make the alkene, or I could get substitution, because I'm running this at like super high concentration. So equilibrium would actually favor acid catalyzed dehydration. Well, we would compare these 3 to each other. So in the IR, I'd expect to see the 3600 binding mode. If I went from this, I'd expect to see a loss of 18 AMUs. If I go from here, I'm going to lose 18, but I'm going to gain 36.5. So that's what, 18.5? It's going to grow up by 18.5 in the mass spec. And if I look at the IR, both of these are going to lose the 3600, but I'll see alkenes and this one, whereas this I really won't see anything. The alkyl halides don't really shift it. So the IR would tell me if I have an alkene, because I could look up the alkene binding modes and it would verify that it lost the OH group because it lost the mode at 3600. But if I run this reaction and basically it looks like butene, I'm pretty sure I don't have an alkene. I just got the substitution. So again, the relative comparisons here, that's the more useful information with mass spec and IR. It is a matter of how you want to use the tools and what tools you have available to you. So in the lab, you did the bromine test. You took Br2 and methylene chloride and added it. That's a lot simpler than running a mass spec and an IR. You can verify that it's an unsaturated product and that you made an alkene. But as far as like, here's an IR spectrum, prove it's an alkene, I would argue you can't do it, because there's a lot of things that can give rise to those peaks. If you, for the same reason you couldn't identify it was is it an alkane or an alkyl halide, there's a lot of things that can shift those peaks beyond just you making that simple substitution. You would need context. Mass spec is the same way, and yeah, unless you have access to a database to definitively prove what you have, you would have to look at relative comparisons. But to look at a mass spec and say, well, is it an alkene? I don't know. No one can know because you could lose hydrogens by making rings. There are other ways to drop that atomic weight that don't involve making alkenes. All right, so that's it in terms of questions I've gotten today. Oh, nope, got another one. Review the last roll on page 29. Oh yeah, I've already gone over this. So yeah, it's just a typo. That should be 1 pentene, not 1 butene. All right, so I've got the chat up. If you got questions, please feel free to ask it. Otherwise, I've got other messages I'm getting. Oh, could I get help on stereochemistry? What are your questions on stereochemistry? Stoichiometry. All right, so limiting reagents. There are lots of ways. There are 3 ways to do this. There is one way I really advocate, but it's a matter on if you're going on to chemistry 2. So if you're in chemistry 1, we've got the 2CH. I guess I should figure all that out. All right, so let me write the problem out. 2CH4 plus 2NH3 plus 3O2 goes to 2HCN plus 6H2O. And 665.5 grams of O2 and 413.9 grams of the ammonia, excess CH4. So there are 2 ways. So I know you got limiting reagent. I'm going to give you the 2 ways that I think work best for figuring out limiting reagent. The first I'm going to advocate for the hardest is what's called extensive reaction. So the way to think about extended reaction is that it is a unitless distance. So a reaction is going to go so far based on the reagents that are involved. And the reagent that carries it the shortest distance, the one that can only carry it so far, that's your limiting reagent. So the way we find extended reaction is we take our 413.9 grams of NH3 and 665.5 grams of O2, and we convert them to moles. And the next step we're going to do is we're going to divide by the reaction coefficient. So in this case, there are 2 moles of NH3 here, and there are 3 moles of O2. And this will each give us the extended reaction for both of them. So I've got XL up, so I've got 413.9. So the extended reaction for this one is 12.2. And the extended reaction for this one is 6.93. So the smallest extended reaction tells you that that's the furthest distance this reaction can go. Now, there's a property of extended reaction with a variable x. That if we multiply the extended reaction by the reaction coefficient of whatever we're interested in, that'll get us back to moles of what we're interested in. So I know now that oxygen is the limiting reagent. And if I want to know how many moles of HCN are produced, I would just take that extended reaction, multiply it by 2 moles of HCN. If I wanted to figure out water, I just take the extended reaction, multiply it by the 6 moles of H2O. So that would give me 13.86 moles of HCN. 6 times that, 36, 40. That's what computers are for. 13.864. Times 6. 41.6. So the reason why we do the 1 here is that it's unitless. So the extended reaction here has no units. Now, if you wanted to just convert, so let's say we took 665.5 grams of O2, and we wanted to go to moles of, let's say, HCN. Convert to moles of O2, and then we would use the mole ratio. So we have 2 moles of HCN and 3 moles of O2. So this is the correct way to do a full conversion. And this is typically how students are taught to do limiting reagents, is you take one of these and you just convert to moles of something else. Well, all of this here is the extent of reaction. So X times my reaction coefficient on the HCN, that's all I've done here. Now the power of the extended reaction is that once we have it, we know how many moles of everything else reacted, but we just multiply this number by whatever is in front. So if we want to know how many moles of NH3 reacted, we just multiply this number by 2. If we want to know how many moles of CH4 reacted, we multiply by 2. If we want to figure out how much HCN, multiply by 2. If we want to figure out how much H2O, we multiply by 6. So if you're just trying to go from mass to moles of something else, yes, you would leave this conversion factor in. But the reason why we like to work with extended reaction, particularly in chemistry too, it comes up quite a bit, is because it gives us an easy way to describe how far the reaction went. And pretty much these reaction coefficients you multiply by, they scale it by that reagent. We know that for every 2 moles of NH3 react, we produce 2 moles of HCN, so we expect them to travel the same distance. But this is going to travel 3 times further. That's just represented here by that reaction coefficient. But yes, if you were just starting out with an oxygen, you take your 6.65, go to moles, use the mole ratio, that 2 to 3, and then multiply by the mass of HCN. So for every mole of HCN, 17 plus 12, 29. Yeah, 29 grams per mole. But for the rationale behind working with extended reaction is that once you have the extended reaction, if you're asked about anything else, you just go back to your extended reaction and work with that. But if you never plan on going beyond Chem 1, I'm not saying this facetiously, like if you don't plan on going beyond Chem 1, stick to this methodology, it makes a lot more sense. If you plan on going to Chem 2, this is a lot more useful. The extended reaction is a lot more useful to work with. You're good. Yeah, been a while since I've taught this. Now for the mole ratios to convert between one thing or the other, it's always where you're coming from, where you're going to divided by where you're coming from. So if you're given CH4 and you're asked to go to H2O, it's always whatever you're dividing by where you're coming from. So the 2 moles of CH4 times wherever you're going to, 6 moles of H2O. And that's your conversion factor. 25.9, yes, cover those at the start. 25, you can't use bromine because it's an anti-addition and it's asking you to give the SEN product. For 29, it's actually just a typo. That should be 1-pentene, not 1-butene. Yeah, you're welcome. All right, so again, I'm here. I'm just getting a little bit of work done. So if you have questions, please feel free to type them in the chat, and I'll answer them as soon as I see them. All right, now we're listening in the chat. So again, these are office hours. These are not lessons. These are not lectures. So if you got questions, please feel free to email them in advance. Orgo students, don't forget your exam is tomorrow, not Wednesday. You should see an announcement on the course website, let you know what room we're in. Same thing as before, come take the exam. We do not have lab after the exams. We are like the only organic section that's on Wednesdays, and so we just had to push your exam up. The B group, you will be coming in next week to complete your lab, so you'll have the full time. It is a synthesis it takes most of the time, which is why we didn't think it was fair as instructors to kind of like make you do a lab right afterwards. So again, exam for Orgo students tomorrow. I will probably, hopefully, have your grades posted before the break. We'll see. It is break, right? So again, if you ever have questions about live streams, please feel free to email me in advance, and I will see a lot of you tomorrow.